Alright, so the first thing I want to do, just getting started, is I want to do a couple of quick bug fixes of things that I've encountered and haven't fixed in the past videos. So the first one is in PageFrameAllocator.cpp. When we lock the pages of the page bitmap, we need to make sure that we are using the page bitmap's buffer address and not the address of the page bitmap variable. The next thing we need to fix is in the kernel makefile. So opening up that makefile, we need to go to the C flags variable and we need to add one more flag in there, no red zone. It's usually okay to use the red zone, but in kernel development it messes with interrupts and can cause some unwanted and unexpected behavior. So we just need to compile that with no red zone. And of course, just to make sure everything recompiles with that flag, just delete our lib folder and then recompile. Alright, now we can go on and start creating our interrupt handler for our PS2 mouse. So we'll jump down into kernel.util.cpp, and it's kind of messy having them all like this. It would be easier if we had a specific function that would create an interrupt descriptor table entry for us. So let's create one now. So right after our IDTR variable declaration, we can create a function setIDTGate, and we need to hand in 4 parameters. The first one is the pointer to our interrupt handler, so void pointer handler. The next one is our entry offset, so that's like our 0xe, 0x8 values. So uint8 entry offset. Then we have the types and attributes, uint8 type and attribute, and uint8 selector, which is our code segment selector that we're using. Right, now we can just copy some of this entry creating code and just change all of the variable names to make sense in this context. So instead of interrupt page fault, we'll just change it to simply interrupt. And we'll change the offset to our entry offset. We'll change this page fault handler to our handler. We'll change types and attributes to types and attributes, and we'll change the selector to selector. Alright, now we can replace this code with our new IDTGate setting function. So set IDTGate, cast it to a void pointer, our page fault handler, our offset 0xe, our types and attributes, which is IDT interrupt gate, and our selector, which is 0x08. And now we can remove this code and do the same for all of these as well. So, alright, now just to make sure that all of that's working, we can compile that and run it to see if anything is broken. But as you can see, everything is still fine. Everything's working just as it was. Now that we've made it easier to create an IDT entry, we can create the entry for our mouse interrupt handler. So we can just copy this code here and change it to mouse int handler. And the offset for this one is 0x2c. And now we need to actually create our mouse interrupt handler. So over into interrupts.h, we can copy our keyboard interrupt handler and create a mouse interrupt handler. And while we're here, we can remove this struct keyword from all of these parameters because it's not required because we're using C++. If you're using C, then you still should keep that there. Alright, interrupts.cpp, remove all of these struct keywords. And now we can create our mouse interrupt handler by copying our keyboard interrupt handler and changing the name. And removing all of the keyboard handling code inside of it. Now, just as a test to get things working, we can print M. Also, since the mouse is on the second pick chip, we need to use the pick end slave so that everything is working properly. And yeah, now we can go about actually enabling the PS2 mouse. Now it's not like the keyboard and it works straight away. We actually need to do some initialization code to get this to work. So over in user input, we can create a new file and call it mouse.h. And we can also create mouse.cpp. Inside mouse.cpp, as usual, just include mouse.h. And in mouse.h, we do pragma once. So inside mouse.h, we need to create a function to initialize the PS2 mouse. So void PS2 mouse initialize. Or rather, we can just do init PS2 mouse. Makes it a little bit easier to type. So then in mouse.cpp we can do void init ps2 mouse. And now we can start writing the implementation for that. So the mouse is on the auxiliary port of the keyboard controller. So we need to enable the device on the auxiliary port, which is the mouse. So to do that, we need to do outb. And to do outb, we need to include our IO functions. So include /io.h. So now we can do outb 0x64 0xa8. And this is enabling the auxiliary device mouse. Now we need to wait to make sure that we can send another command to the mouse to make sure that we're not sending messages too quickly. So let's create a function called mousewait, void mousewait. And then we need to wait until bit number 2, as we see here on the OSDev wiki, we need to wait for bit 1, which is the second bit, of port 0x64 to become clear before we can send more bytes to port 0x60 or 0x64. So we'll just check to make sure that bit is clear. So if in B 0x64 and 1, then we can return. Otherwise we can get stuck in a loop, so while, and we can create a timeout. So uint 64t timeout equals 100,000. So we'll wait for 100,000 loop cycles to return from this function. So while timeout minus minus, we keep checking for this bit to be cleared. So now we can use that mousewait function to check if we can send another command to the mouse. So we need to do mousewait. Now we need to make sure the status byte of the mouse controller is correct so that it sends interrupts when we need them. So we do outb 0x64 0x20, which tells the keyboard controller that we want to send a command to the mouse. And now we need to wait until the bit 0 of port 0x64 is set until we can read from port 0x60. So we need to create another mousewait function. We can just copy this first one and we can call it mousewait input because we're waiting to be able to read the input, and this is in B 0x64 and 0. If that is equal to 1, then we can return. Otherwise we just wait for our timeout. So now we need to wait for mousewait input. And then we can read from the status byte. So we can store that in a uint8 status equals in B 0x60. And now we need to make sure the second bit is set. So now we can do status. Now we need to do status or equals 0b10 to make sure that the second bit is set. And now we need to set the status byte back into the controller. So we need to wait to be able to send the mouse some input. Then we need to do outb 0x64 0x60 to tell the controller that we're about to send a command to the mouse. Now we need to wait to make sure that we can actually send our input. And then we do outb 0x60 status to load that new status byte back into the mouse controller. So all of this is setting the correct bit in the, which is the compact status byte. If you'd like to learn more about what this is and what it does, there's a link in the description to the OSDev wiki article. Now that we've done that, we can tell the mouse to use default settings. So let's create a function to send a command to the mouse. So void mousewrite. Now we can just expand this and do this the long way, but doing it this way with the mousewrite function is a little bit easier. And we want to send it the value. So I need to wait to make sure that the mouse can receive some input. Now we need to tell the mouse that we're sending a command. So 0x64 0xd4. Now I need to wait to make sure we can actually send it, and then we can send the command 0x60 and then value. Now we can use that function to tell the mouse that we want to use default settings. So mousewrite 0xf6. 0xf6 is the default settings for the mouse. And now we need to get the acknowledgement from the mouse that that has happened. And to do that, we need to create another function, which is mouseRead. Now we need to wait if we can get input, so we need to do the mousewait input function. And then we can return in B 0x60. 0x60. So now after we've written to the mouse, we need to read from the mouse to make sure that we get the acknowledge so that the mouse controller can continue. And then to enable the mouse, we just send a command 0xF4. And then we get the acknowledgement again, so mouse read. Now up here in mouse wait, we need to make sure that this in B and 1 equals 0, because we need to make sure that this bit here is clear, but in mouse wait input, as it says here, we need to make sure that the bit 0, so the 0th bit, is set. That'll work just fine. So just here in our mouse wait functions, instead of 1, this needs to be 0B10, and this one needs to be 0B1. So we're selecting the first bit here and the second bit here. Now we can call our initialize ps2 mouse function inside of kernel-util.cpp. So after prepare interrupts, we can do init ps2 mouse. And of course in kernel-util.h, we need to include our mouse.h. So user input mouse.h. There we can call this function correctly. And our bit masks here, we need to unmask another bit. So we'll move that out until we've done all of the initialization so nothing goes wrong. And we need to set this bit clear here. And this is the cascading bit, so that allows interrupts from the second pick chip to go through and be registered on our system. And then the keyboard interrupt on this is this bit here. So 3 ones, 0, and then 4 ones. The last thing we need to do is read from the 0x60 port to make sure that the mouse is emptying its buffer so that it can send a new interrupt through. So mouse data equals in B0x60. Now as you can see, when I move my mouse, it displays lots of M's to the screen, so we are successfully getting our mouse interrupts. Now we can stop it from printing M because that's not really what we want. One thing I'll also do is move this ASM_STI call, which is re-enabling the interrupts, right to the end of our initialize kernel function, so that we're only enabling interrupts once all of the initialization is complete, just to make sure that nothing unexpected happens down the line. Now that we're getting interrupts from the mouse, we can actually do something with the information that it provides for us. So over in mouse.cpp, we can create a handle mouse function. So let's call it void handle ps2 mouse, and we can take a uint8 data, which is the information that we get from the interrupt when we read from the IO port. Right, so the data from the mouse comes in multiple bytes. So every time the mouse wants to send some information through interrupts, it will send 3 or 4, depending on the configuration, interrupts, and it will send a packet of 8 bits every time. So what we need to do is get all of these bytes and put them together into one single mouse packet, which we can then handle once it is full. So we need to create a uint8 mouse cycle, which equals 0, so that we can keep track of which byte we are currently at. And now we need to do a switch case using that mouse cycle. So switch mouse cycle case 0 break, case 1 break, and case 2 break. Alright, now we need to create an array. So we have a uint8 mouse packet, and this is an array of size 4. The way that we've configured our mouse is so that it will only send 3 bytes, but we can also configure it optionally to send 4 bytes, and the 4th byte contains information about the scroll wheel and also the 4th and the 5th mouse button. Currently we only have information about the X and Y movement of the mouse and the left, middle and right buttons. But in this tutorial we'll only be handling the first situation with the 3 bytes rather than the 4 bytes, just for simplicity. We also need to make a bool mouse packet ready equals false. And we'll just make mouse cycle uppercase. Right, so on case 0, if mouse packet ready, we want to break, because if our mouse packet is ready, we don't want to change what is already in the mouse packet, because that will corrupt anything that's currently using it. And now we need to do mouse packet 0 equals data, and then mouse cycle plus plus. Alright, so now let's take a look at what's actually inside this first byte. So as you can see here, byte 1, these are all the bits that are inside of it. So we have left button, right button, and middle button. We have this 4th bit, which is always set. Then we have the X sign and Y sign, which is to tell if the movement is negative or positive. Then we have y overflow and x overflow, just to tell us whether the movement has overflowed or not. So technically movement is a 9-bit value. Right. So the first byte, we have this bit that is always 1, so we can use that to check if the packet has become out of sync, because sometimes with the PS2 mouse controller, these packets will come out of sync. So we just need to make a little test if data and 0b00001000 equals 0, meaning it is not the correct byte because it is not always 1, we can break. Alright, now with case 2, which is the X movement, we can just store that value into the mouse packet. So mouse packet 1 equals data, and then mouse cycle plus plus. And now we can also do mouse packet 2 equals data and mouse packet ready, because we have handled all of the different bytes that we can get. So mouse packet ready equals 2 and mouse cycle equals 0. Also, we need to make sure that we're checking if the mouse packet is ready in each of these cases, so that we aren't corrupting this mouse packet while it might be in use. Alright, now in interrupts.cpp, we can call that function. Well, we're going to have to declare it in our mouse header first, so void handle ps2 mouse semicolon in our header, and then inside of interrupts.cpp, we can now do handle ps2 mouse. And of course, in interrupts.h, we're going to need to include our mouse header. Alright, now that we're handling the PS2 mouse and creating the packet for us to use, we also need to pass this mouse data to handle PS2 mouse. We can now handle this packet on the main loop in the kernel. So inside kernel.cpp, we can create another while loop. So while true, so this is the main loop of the kernel. We'll do lots of operations in here that don't necessarily have to be time sensitive. Now we can do ProcessMousePacket. Now we don't have this function yet, we're just going to declare that in mouse.h now, so void ProcessMousePacket. And in mouse.cpp we can now write that function, so void ProcessMousePacket. Alright, now we need to check if mouse packet ready is not ready, so if this is false then we can return, otherwise we can set it to false, which will then allow this PS2 mouse handler to fill the mouse packet with some new data and then set it to ready once again. Now back in mouse.h, we're going to need to define some values. So define PS2 x sign 0b00010000, and this is so that we can target this x sign bit here. We need the y sign, which is 001, and then the rest is zeros. We have the X overflow, which is 0, 1, and then the rest is zeros. And then we have the Y overflow, which has the most significant bit as 1, and the rest is 0. We can also target these button presses as well. So define PS2 left button, and this has the least significant bit set to 1. The middle button has the second least significant bit as 1, and the right button has the third least significant bit as 1. Alright, now that we have those defined, we can now check and see what values we are getting in our mouse packet. So we can define some bools, so x negative, y negative, x overflow, and y overflow. If mouse packet 0, indexed by 0, and PS2 x sign, x negative equals true, else x negative equals false. And we can do that with the y sign as well. PS2 y sign, y negative equals true, else y negative equals false. Now we can do the same with the x overflow and the y overflow. If the PS2 x overflow is true, then x overflow equals true, otherwise it equals false. And if the y overflow, then y overflow equals true, otherwise y overflow equals false. Alright, now we can start moving around the mouse position using the values contained in the second and third byte of our mouse packet. So if x negative, well, if it is not negative, then we can do mouse position, which we haven't created yet. So at the top of mouse.cpp, we can create a point, mouse position. Inside of mouse.h, we can include /math.h, and we can extern point mouse position. So now we can do mouse position.x plus equal mouse packet 1. And if x overflow, then mouse position.x plus equals 255. And this needs to be an uppercase X. Right, now we can do else, in which case it is negative. We can copy these and change this plus to a minus. Alright, now we need to do the same with the y values. So just copy all that, paste it in, and change all of the x's to y's. And we need to change this mouse packet to mouse packet 2. Right. Now, one thing about the Y value is that when you move your mouse down, it will move the mouse towards the top of the screen unless you do the opposite of this operator here. So all the pluses here need to be minuses and all the minuses need to be plus. So we're inverting the Y axis, or else our mouse will be basically upside down. Now I need to make sure the mouse position doesn't go below or above our frame buffer. So below 0 or above the width and height. So if mouse position.x is less than 0, mouse position.x equals 0. If mouse position.x is greater than our global renderer, which we need to include using basic renderer, global renderer.targetFrameBuffer.width -1. So if it's greater than the width -1, then it needs to equal the width -1. And this x needs to be uppercase. Right. Now we need to do the same with the y values, so just copy those and replace all the x's with y's and all the widths with height. So we have this width becoming height, and this width here becoming height as well. And now, just to be able to see where our mouse is visually on the screen, we need to print to the screen. So, global renderer, print, and I will just print an A, or rather we can do global renderer put char, and I will put an A to the screen, and we need our mouse position.x and mouse position.y. This here needs to be mouse position x. And just for our little test here, we can't do -1 because if we try to put a char so close to the edge of the screen, it will try and put pixels outside of the frame buffer and cause a page fault. So we just need to put a little bit of a test in here. So instead of -1, we -8 to make sure that we have enough room to put the character. And for the y value, we need to put -16. So I've made a little mistake here. This mouse packet, we need to actually change the mouse packet completely if it is negative. So the mouse packet, the first byte of the mouse packet now equals 256 minus itself, or indexed by 1. And that just resolves the movement correctly. And we need to do the same with the y negative. So mouse packet with byte 2 equals 256 minus mouse packet indexed by 2. Now if we compile and run that, we should be able to move our mouse across the screen, and wherever the mouse is, it draws an A. Alright, so as you can see, I can move my mouse around the screen and it draws an A wherever I go. So that's pretty good. Obviously this isn't a full-on mouse pointer, but it's just a proof of concept that we've got the mouse interrupts working and we are handling the packets correctly. Eventually we'll be able to implement a mouse pointer, but that's a little bit more technical than just drawing an A to the screen wherever the mouse is. So we'll be getting onto that in a future video. But for now, thank you for watching and I will see you next time.